Hi, Victor Morganda here from Fact Engine. We're going to have a look at relational knowledge graphs and the theory behind relational knowledge graphs. And we're going to do that through the Boston conceptual modeling software by Fact Engine. So this is Boston, and Boston is a productivity tool for relational knowledge graphs or graph-relational databases, or multi-model databases or poly-model databases. Now, they're not all exactly the same thing, and by looking closely at what a relational knowledge graph is, or the graph-relational model, you'll get a better feel for the difference between those types of databases and multi-model or even poly-model databases. To do that, to look at the theory behind relational knowledge graphs, we're going to do it in a manner that makes it as exciting as possible. And the most exciting thing about a relational knowledge graph is that the entire database is looked at as if it were either a graph database or a relational database. And relational knowledge graphs mandates that you dispense of the notion of either a graph database or a relational database, and you look at your entire database as if it is either or a graph or relational database. We've got a model in front of us, and we're looking at a property graph schema for a cinema seat booking database. Now, I'll show you a picture that'll probably paint the picture of the schema, and where we've got a lady who's making a phone call to book a seat, and here's her booking ticket that she's picturing to watch a movie. In her mind's eye, she's already seated at the cinema and she's got a popcorn in front of her. So she's booking a seat at a cinema to watch a film. Now, if we go back to the model, we can see that we have a person who can make a booking for a seat in a row in a cinema. And the booking is for a session to watch a film at that cinema, and where the seat can be in a section such as, say, a deluxe section or something like that. Now, it becomes a property graph schema when we look at the properties against each node type in this property graph schema. So where a film might have a film ID and a name, and where a person might have an age, a date of birth, we've got a second age against this particular model, and a login name. And where a seat is in a cinema and has a row number, a letter, and it's in a section, it has a section name. Now, with the relational knowledge graph paradigm, we can look at the same model as if it were a relational database. So we have a look at the entity relationship diagram for that same model, and where we have booking and a person and a seat and a section and a row and a cinema. We have these tables, which are many-to-many tables in our relational model. Say booking has seat, where a booking can have many seats, and a seat over time can have many bookings. And this is a many-to-many join table, as everyone will be familiar with in a relational database. Now, if we morph back to our property graph schema, you'll see that morph into a edge type between seat and booking. So this edge type has an isomorphic mapping or a homomorphic mapping to its corresponding table in our relational model. Now, with a relational knowledge graph, most businesses that are implementing relational knowledge graphs implement them over the top of a relational database or an ostensible relational database. But it doesn't really matter, because if we picture our relational database as if it were a graph database, we can go the other way around. So you could implement a relational knowledge graph over a graph database, and there'd be design and architectural decisions as to which way you go with that. This particular model in Boston is sitting over the top of a database, and it's called our Cinema Bookings database. If you look on the top left-hand side, we can see that we've got a Cinema Bookings model, and we're looking over the top of a database. If I go to, say, Film, and view the data behind that node type, we can see that there's a range of films in there. So Rocky, Grease, Dr. Zhivago, Inception and Speed. I can go to Person and look at the various people that we have in the database. So Peter, Paul, Mary, Simon. I can look at the bookings and see which bookings have been made. So these bookings, that's the data for the bookings that have been made. So we're looking at a model over the top of a database. And the type of model that we're looking at is a relational knowledge graph. Now, why is this any different from, say, a multi-model database or a polymodel database? There are already extant multi-model databases. The difference is that with a relational knowledge graph, we're not storing graph type data away in a JSON field on a relational database table somewhere. We're treating the whole database as if it were already a graph database. Now, just to prove the theory, when we look at this model in the Model Explorer and we look at its model configuration, the database that it sits over is an SQL-like database, so a relational database. And this is the path to that relational database on my OneDrive folder, and here's the name of the SQL-like database, so cinemabookings.db. I can test that connection. I've got a successful connection to that database. So, although we're looking at a property graph schema, we're looking at it over the top of a relational database. Now, I can make this look more like a relational database, a property graph schema that everyone's familiar with by changing one configuration item. I'm going to say, let's use the Neo4j style edge labels, and hit OK. And I'm going to close that page and reopen it. Now we can see the property graph schema in a fashion that's very familiar to everyone. So where our predicates are in uppercase, and we've got underscores before words, and we're saying booking is for seat, seat is at cinema, row is in cinema, etc. So this is a property graph schema for a traditional graph database, but we know that under the relational knowledge graph model, we're looking at a relational database in this instance that has a relational schema. So this entity relationship diagram is for a relational schema, and it's sitting in this instance over a SQL-like relational database. We get a real feel for the relational knowledge graph model when we start running queries over the database. Now let's write a graph type query over the top of that database. Let's write this query. So which person made a booking that is for a seat that is in a row that is in which cinema. So that's a graph type query where we're traversing the graph and we're going for the worst possible join we can do here. We're saying a person, we want the people that made a booking for a seat in a row in which cinema. So we're traversing this graph here to get our results. Which person made a booking that is for a seat that is in a row that is in which cinema. Now I'm going to hit go on that and get our results. So here's our results. So Peter made a booking for a seat that's in a row in the Great Western Cinema. Paul made a booking for a seat that's in a row in the Great Western Cinema. And Peter again made another booking that's in a seat that's in a row in the Great Western Cinema. So we've run a graph query against our relational database and we've got our results. Now let's have a look at something really interesting. Here's our results, but here's the query that returned those results, and it's a SQL query. So this query in SQL does the traverse from person to booking to seat to row to cinema. So we've converted a graph query to an SQL query to get our results. Let's have a look at something really exciting now. I'm going to grab a Cypher query. So those familiar with graph databases know that Cypher is a graph query language for graph databases. I'm going to change our query type to Cypher, and I'm going to run this Cypher query, so this graph query, over our relational database. Now it's the same query, so we're saying match person that has a booking, and we've got the edge in reverse here, so the is for, so booking is for person, but we've got an arrow pointed to person. So we're saying match the person who has a booking that has a seat that is in a row that is in a cinema, and we want to return the login name and the cinema name. So it's a Cypher query. We're going to run a graph Cypher query against a relational database. And here's our results. So we get the same results. So Peter has made a booking for a seat in a row in the Great Western Cinema, and he's done that twice. And Paul also has made a booking for a seat in a row in the Great Western Cinema. Now when I go back to the query here in Boston and Fact Engine, here's our Cypher query. I'll just get rid of that, but it's also converted that query using a transpiler to a relational query. Now I need to do a little bit more optimization on the transpiler, but if I change, that's why it's looking very long there, if I change back to SQL and run the query, we get the same results. And we have to run an SQL query against this particular database because it is a relational database, a traditional relational database, sitting underneath our model inside Boston and Fact Engine. So just to recap, we've got a SQL-lite, traditionally a relational database, that we've run graph queries against that relational database. And where relational knowledge graphs are databases that implement a graph paradigm over the top of relational databases, or from the ground up are built as relational graph databases or graph relational databases from the ground up, and where the query engine is optimized for graph queries. So in this instance, we've effectively turned a SQLite database into a relational knowledge graph. Dedicated relational knowledge graphs will optimize queries, especially for graph type queries where we're doing long traversals across the graph. So where does this position relational knowledge graphs at an architectural level when competing against marketing and hype campaigns from companies that either are pushing a relational database or a graph database and pushing them as separate things that aren't one and the same thing? I'm going to dive into that because I feel it's very important. The notion that a graph database specializes in highly connected data as opposed to relational databases is, in my mind, complete rubbish. When we look at the realities on the ground, that the moat that graph databases have is something that isn't much of a moat at all when we consider that it is the schema that defines the way we look at a database, and at the hardware and in-memory architecture, there is nothing to stop a otherwise relational database sucking data off hard drives or solid state drives or what have you into memory, and in memory storing the model as if it were a graph database, and where the database, the relational knowledge graph, is completely optimized for doing graph type queries in the most optimal fashion. And so, for instance, with Neo4j having the graph model in memory, so the data in memory, optimized for graph queries, there's nothing to stop a SQLite database in the future from having all of its data, well, as much as possible in memory, and where queries are optimized for graph type traversals of the graph. Now, you might say, well, that's a big job. Well, not really, and I'll explain why. If we look at the relational model, we've seen how trivially easy it is to treat a many-to-many table as if it were an edge type in our property graph schema. The same is true for foreign key relationships. So where, say, seat is in row, and if I have a look at seat and I go back to its relational model, you'll see that it has a foreign key relationship to row. Now these relations, these foreign key relationships or relations, are ostensible edges. Now, if I'm lucky, I should be able to just click on that edge and see its edge type. Now, I couldn't do that, but let's have a look at the object role model. For the same schema, where a seat is in a row and where this fact type is the foreign key relationship. If I look at its properties and have a look at its database name, that's its edge type there, is in. So that is in label is our is in edge type label, but we're talking about exactly the same thing. This edge type is this foreign key relationship, which is in our object role model our fact type with the database name of isIn, so that when I run my Cypher query, I'm running it against a model that converts it to either SQL or Cypher, because we don't have to have a SQLite database or an Oracle database or an SQL Server or a Postgres database. We could even have a Neo4j database being treated as if it were a relational database, but our queries in Fact Engine would then need to be in Cypher. So the moat of saying that graph databases are something different and are highly optimized for highly connected data isn't much of a moat at all if those who otherwise develop relational databases sit down and truly optimize their queries for graph traversal, and that's happening pretty much across the board on a daily basis anyway. Lately there's been some talk about a special algorithm called a dovetail join algorithm that effectively implements a breadth first type algorithm for graph traversal on relational databases of sorts, and where even that isn't such of a moat because the algorithm has been published, and so any relational database can implement a dovetail join to affect database queries that traverse multiple hops in a very efficient fashion, as if we were working with a graph database. Now, what does that say? Well, it says that in the future, where the puck is going is that you're not going to have to care whether or not at the hardware level you have what's known as a graph native database or a relational database, because the way technology is going, with those database vendors who really know what they're doing, they'll make their database just as fast as if it were a graph or a relational database, and you'd never know the difference. And so that's where we get to the notion of a relational knowledge graph paradigm. Now, to really cement the point, let's have a look at the meta model behind this property graph schema. So I'm going to right click on that. I'm going to, forgive me, I'll just come back in one sec. If I right click on this page, this property graph schema, and view the meta model behind that, here's the meta model of our property graph schema. And what I'm going to do is I'm going to change the language of our meta model. So this meta model is being viewed as an object role model. I'm going to change it to an entity relationship diagram. I'm going to close that page. I'm not going to save it. I'm going to close that property graph schema page. Now notice that it's called PGS new model page 1, and I'm going to reopen it. So I'm going to double click on PGS new model page 1, and now it opens as if it were a entity relationship diagram. So this has exactly the same meta model as our property graph schema, and I can prove the point again by changing its language to back to property graph schema, closing that page. Now I'm going to reopen the same page, PGS new model page 1, and it reopens as a property graph schema. What does that tell us? Well, it tells us that the meta model, believe it or not, for a property graph schema is practically exactly the same as a entity relationship diagram. Now there's some people who are going to really struggle with that, and some people get really angry about that, but that's the reality. And how do I know? I wrote the software. So our property graph schema meta model is for all practical purposes the same as our entity relationship diagram schema at the meter model level. And if that's the case, why don't we just treat any database as if it were a relational database or a graph database? So let's recap. We've got a SQL-like database called Cinema Bookings, which ostensibly is a relational database. We're effectively turning it into a relational knowledge graph, where we're looking at a traditional property graph schema over the top of our relational database, where we can write cipher queries as if it were, say, a Neo4j database, and execute those queries against a relational database and get our results. And in this case, we're turning our cipher query into a SQL query because we know that the implementation of SQLite at the software level is as if it were a relational database with an entity relationship diagram. And that is our paradigm for relational knowledge graphs, where graph databases are implemented under a otherwise relational model. So we can morph from our entity relationship diagram, from our relational model, to our property graph schema model, and know that deep down we're talking about exactly the same database. Thanks for watching. I hope you enjoyed the video. I'll see you in the next video. Thanks.